All right. Yeah. So thanks so much, Dirk, for the introduction and for the kind invitation also to speak with everyone today. So yeah, good afternoon to those of you in the US. Good evening to anyone in Europe. Good morning to anyone who might be over my side of the world. It's not quite as early as Dirk made it sound. It's 7:30 in the morning, so it's not it's not too bad. All right. So today, rather than, I suppose, focusing on cross-linguistic diversity, which is, as Dirk said, one of my sort of main areas of research focus, I'd like to talk about, I suppose, a different sort of source of diversity with regard to language processing, focusing more on individual differences and changes across the lifespan. But our story begins basically back in the 1990s, so almost 30 years ago now, where a really interesting study gave rise to some quite intriguing findings. So some of you may have heard of the Nun Study, which, as its name suggests, actually was basically a study of cognitive aging and Alzheimer's disease with a group of North American nuns. And one of the interesting things that came out of this study from a sort of language perspective was basically the idea that linguistic ability in early life, meaning sort of in early adulthood, may be related to cognitive function and even sort of the risk for neurodegenerative disease in older adulthood. So the way that this was actually studied was by examining these autobiographical texts that the nuns had written when they first entered the convent in their sort of early 20s usually. So I'm not entirely sure why they had to do this. Possibly it was sort of part of the nun application process at the time. But in any case, the researchers on the Nun Study had access to these texts from a number of the nuns that they studied, and they looked at a variety of different sort of linguistic complexity measures, including some grammatical complexity measures, but also a measure called idea density, sometimes also known as propositional density. And this basically refers to the average number of ideas expressed per 10 words or propositions. Ideas or propositions here are operationalized essentially as predicates, so things like verbs and adjectives, negation, all of these will basically count as ideas. And you can just sort of see here, I don't want to go too much into the details of how the calculations work, but you can just sort of see a comparison here between two sisters who were basically very low scoring in terms of idea density, sister A here, and very high scoring sister B. Okay, so what Snowdon and colleagues concluded, and it's quite a strong conclusion, is they say our findings support a strong relationship between cognitive ability in early life, as indicated by linguistic ability, and cognitive function and Alzheimer's disease in late life. Low idea density in autobiographies written at an average age of 22 years significantly increased the risk of both poor cognitive function and Alzheimer's disease 58 years later. So that is really quite a striking finding, right? I mean, if we're able to potentially already derive a measure of the risk of something like Alzheimer's disease from text that people write, and assuming that this is actually linguistic ability that we're seeing reflected here in early adulthood, that would be quite a striking way to, potentially change the prognosis, right, for something like Alzheimer's disease. So what's actually at work here? I'll basically just sort of start by talking about what was suggested at the time, right? Because the spoiler for, I guess, the rest of the talk is we still don't really know. But basically, one of the early ideas was that idea density might actually be something like a marker of linguistic efficiency. So this was something that was proposed by people like Susan Kemper and her colleagues. So they proposed, for example, in a 2001 paper that low P density, so they basically abbreviated it as P density for propositional density, in young adulthood may reflect suboptimal neurocognitive development, and that this then in turn might increase susceptibility to age-related decline due to Alzheimer's or other diseases. So again, quite a strong claim, right? Saying that from this linguistic measure, we might be able to have some sort of a sense of people's neurocognitive development. The reason they thought it might reflect this was basically that they assumed that idea density reflects the efficiency of linguistic encoding. So how succinctly ideas are packed into sentences, right? The idea is if you've got a high number of ideas of propositions per 10 words, then you're encoding a lot of information, right? If your idea density is low, then there's not a lot of information density sort of going on there. Some of these early studies also showed that idea density correlates with vocabulary measures, reading rate, and verbal fluency. By contrast, it didn't seem to be related to high school grades or educational attainments, which some people still find surprising. And it turns out that results on age-related changes are mixed. So again, there are some studies that suggest that idea density declines over the course of the adult lifespan. There are other studies that show slightly different things. We'll get back to that a little bit later. Now, if you're wondering how representative this kind of result is, given that the participants of this study were all nuns, the Nun Study findings were replicated in some later studies, for example, with data from the Johns Hopkins precursors study. So this study was with Johns Hopkins medical school students who, however, were all male. So again, a highly skewed sort of population, but different to the nuns. So at least it doesn't seem to be just an effect that we find in nuns. So really, the question is, what's actually going on here? Can we shed some light on perhaps the neurocognitive or even sort of neurobiological mechanisms that might be at play here? And when we started thinking about this, we turned to this idea of active inference and predictive coding, which I assume most of you will be familiar with. So sort of the idea that very broadly put, the brain is a prediction machine which actively infers the causes of its sensory input, and that this might provide sort of a unified theory of how the brain works, right? Basically this idea that we're constantly using an internal model of the world to predict upcoming sensory input, and then if that sensory input doesn't match the model, we have to sort of update the model. And then of course there's the whole link to action as well, which I won't go into today. So we reasoned that if idea density is basically a measure of sort of the efficiency of linguistic encoding, perhaps it might actually serve as a measure of linguistic model quality. This was our hypothesis, right? So the idea that people with high idea density might have, very high quality sort of predictive models as they're processing language. That was sort of what we wanted to explore. Now, another reason, Dirk also mentioned the neurobiology of language in the introduction. Another reason why my colleagues and I are interested in this sort of model of active inference and predictive coding is that it does have quite a strong neurobiological grounding, right? Right down to the sort of level of microcircuits. I'm not going to go into the details here, but I think it does make it attractive as a potential sort of basis for the neurobiology of language, because there are at least some theories. Of course, these are theories, right? But there are some theories, some quite detailed models about how this sort of cognitive architecture might actually relate to neurobiology. In terms of what we're going to be talking about today, though, another aspect of this type of sort of predictive coding architecture is actually going to be quite important, because it relates to the way in which the sort of model information and the sensory evidence are combined with one another to update one's beliefs. So basically, it's not just the case that whenever there's a prediction error, so when there's some sort of sensory input that doesn't match the prior belief, that doesn't match the model assumptions, that there's always the same kind of model updating that takes place. This is rather based on the so-called precision weighting of the prediction error signals. Now, precision weighting essentially refers to the certainty or uncertainty that's ascribed to the model and the sensory input, with precision being the inverse of variance. So basically, if you've got high precision evidence, then you've got, essentially, say, high quality sensory evidence with low variability. Now, let's just have a quick look at this sort of schematic figure from Adams and colleagues 2013. So imagine this is sort of the, the sort of the distribution associated with the model, with the prior belief. Then we get some sensory evidence that comes in associated with, this quite broad distribution here. Then we might, sort of shift our posterior belief, so update our model to converge on this slightly shifted distribution, so moving towards the sensory evidence. But here you can sort of see that the sensory evidence is still somewhat noisy. If the precision of that sensory evidence increases, then we'll be more likely to shift our posterior belief more strongly towards that sensory evidence and away from our prior beliefs, right? Our prior assumptions. An example of this, very sort of simple example of this might be processing speech in noise, right? If you have a prior belief about what you're expecting someone to say and they say something surprising, if you're listening to them via, say, a poor Zoom connection, which hopefully you're not doing right now as you're listening to me, you might be less likely to actually assume that they said what you thought you heard, and you might be more likely to actually trust your prior belief, to trust your model, right? But if your sensory input of the speech is crystal clear, then you might be more in this kind of situation. You might be more inclined to actually veer away from your original assumptions and trust the input, so to speak, right? So the idea is that the way in which we update our models is going to be based on the precision both of the model itself and of the sensory input that comes in. And this is going to be relevant because if we're sort of talking about this idea that, idea density might be related in some way to the quality of a predictive linguistic model, then it might conceivably sort of vary the precision with which we're going to be updating our model. Or sorry, the precision of the prediction errors is what I should have said, and hence the way in which the model is going to get updated. So how can we measure this kind of precision-weighted prediction error signal? This has been studied quite extensively using the mismatch negativity, or MMN, which has been described particularly within this sort of predictive coding context as an index of sensory learning. And the MMN shows a sort of a very nice property, which is that if you change the sequences of standards and deviance in a sort of auditory oddball paradigm, where of course we then see MMN effects showing up for deviance versus standards, right, in that kind of paradigm, then MMN amplitude, measured as the difference between deviant and standard, increases with increasing sequence length. And the idea is that this sort of reflects increasing rule stability, right? So if you have a longer sequence where people are able to get used to which stimulus is the deviant, which is the standard, then the predictive model is going to be stronger. Hence, you see a larger MMN, right, with essentially with higher precision of the predictive model. So you can just sort of see that here. This is from a study by Todd and colleagues in 2011. So you can see here the speed of sequence change, so fast, medium, slow, and you can see that the longer a sequence has to stabilize, the larger the MMN amplitude, the more negative. There's also a bit of an effect here of whether a sound was first encountered as a deviant or as a standard. So there's a bit of a primacy effect going on here as well. But in general, the pattern is that as a predictive model has time to stabilize, precision is higher, you see a more pronounced MMN. So the MMN has been taken as a sort of potential electrophysiological signal of precision-weighted prediction errors. Now, we've argued in our research in relation to language that we can actually think of the N400 as a very similar kind of signal. So essentially as a longer latency MMN, reflecting something quite similar in the sense that we could view it as an electrophysiological marker of precision-weighted prediction errors in language processing. And really the reason why it's different to the MMN is mostly, glossing over a few things here, but is mostly because the input is more complex. So in a very simplified sort of schematic view, the idea would be, we have our analyzed input, sensory input, which is matched against the predicted input, but the way in which any kind of prediction error that occurs here then leads to internal model updating is modulated on the basis of that sort of precision weighting, and N400 amplitude changes depending on that precision weighting. So this was actually, in fact, something that we came up with primarily on the basis of cross-linguistic results. I don't have time to go into that today, but the idea was basically that the precision of certain information sources changes depending on their role in a particular language, and particularly how reliable they are essentially as cues for interpreting sentences in a particular language. So that was sort of how we came up with this idea. But we thought, well, it might actually also be an interesting idea to examine in terms of inter-individual variability. So if in general we have this sort of system that has a sort of a variable weighting with regard to how much we're going to be relying on our prior model assumptions vis-a-vis the incoming sensory input, if there's a mismatch, right? Which one essentially do we weight more strongly depending on the precision? Then this conceivably could also be something that varies between individuals. So there might be some individuals who have a higher propensity to sort of trust their internal model. And on the other hand, there might be some individuals who have a higher propensity to update their model more frequently. So that was what we were sort of interested in having a look at. There's a bit of literature on this in non-neurotypical populations, for example, in schizophrenia. So it has been shown that people with schizophrenia show reduced MMN amplitudes. And Adams and colleagues, for example, argued that this is due to less precise top-down predictions that render everything relatively surprising. So basically the idea is he wouldn't get that sort of attenuation of the MMN for the predicted standard because everything tends to be quite surprising, right? So there's no sort of distinction between what should not be surprising and what actually is surprising. So because this is thought to include sensations that should not be surprising, such as self-generated actions, this then has been used to explain some of the symptoms of schizophrenia, like delusions of control, things like that. So this is just a one study that showed this sort of effect. So here was a group of people with schizophrenia, and it was basically a longitudinal study where we have two MMN effects shown here at two different time points. So basically time point 2 was where essentially their condition had progressed. And we can sort of see that with that progression, we see a reduced MMN amplitude, whereas for a control group, there was no difference between those two time points. This type of sort of variability has also been examined with regard to aging. So there was a study by Moran and colleagues published in 2014, where this was also an auditory oddball MMN study. And Moran and colleagues basically argued that older adults show a higher reliance on prior beliefs and less sensory learning. So the idea is that as we get older, we might update our models less frequently, which basically means that we avoid overfitting. We're able to get by with less complex and more efficient models. And the reason we can do that is because we've accrued experience with our predictive models over the course of a lifetime. So our models are pretty good, right? We get by without updating them too frequently. Of course, we still have to update them, otherwise we'd be completely out of touch with the world around us, but we don't have to do it as frequently. And this was essentially described as the brain aging optimally to model its environment. And it turns out with a sort of a DCM-based model of the MMN, you can actually predict age quite nicely, which is sort of a pretty cool finding, I think. So given that there is some evidence in the literature that different populations based on, for example, non-neurotypical populations or also lifespan changes might show differences in weighting of the prior belief in comparison to the sensory information in the case of a predicted error mismatch, we wanted to have a look at whether we can find evidence for similar variability in terms of inter-individual differences in predictive coding mechanisms in language, and whether, to start with, we could do so in young, healthy adults. So in this initial study, we looked at several individual differences predictors, idea density for one, so based on what I was saying before, the hypothesis that idea density might tell us something about the quality of a predictive linguistic model. And we also looked at some resting state EEG-based measures, including aperiodic or 1/f slope, and also individual alpha frequency, which I'm not going to talk about today. Now, just a brief note on aperiodic slope, in case you're not familiar with this. So basically, there's a general phenomenon that lower frequencies in the human EEG are associated with more power. So this approximates 1/f power law. And you can sort of see that here if you've got a power spectral density plot. So we've got frequency on the x-axis and power on the y-axis. You can see that as frequency increases, power decreases. Okay, and the sort of the linear approximations here, this is what you can think of as the aperiodic or 1/f slope. It has been shown, for example, by Wojtek and colleagues that this slope flattens with increasing age, as you can also see in this diagram here. And this has been associated with levels of increasing neural noise. Now, neural noise in this sense is defined in terms of increased levels of aberrant or background firing, so less synchronicity of activity in broad brain networks. And it's also been linked to an increased excitation to inhibition ratio, so essentially less inhibition associated with a flattening slope. Now that sort of, that sounds bad potentially, and neural noise sort of already evokes this, something we don't want kind of a feeling. But Wojtek and Knight actually proposed that in moderation, it can actually be a really useful mechanism, namely sort of a control mechanism to protect against hypersynchronization, which occurs also sort of in certain patterns of disease. So of course, we don't want too much neural noise, but yeah, a little bit of noise seems to be a good thing because it protects against this sort of hypersynchronization in neurophysiological terms. So just like you to sort of keep that in mind because it will become important later. Now, in relation to language, a study by Dave and colleagues out of UC Davis, also, I think they were actually the first to look at aperiodic slope in relation to language processing, and they came to the conclusion that we actually see stronger predictive language processing as measured, for example, by the N400 with steeper aperiodic slopes. So that was sort of the first indication as to why it might be interesting to look at aperiodic slope in relation to predictive language processing, in addition to our idea density predictor, which we had sort of come up with on the basis of the Nun Study and those associated studies that I talked about. Now, for the study that we ran, we presented our participants with these short sort of 4 to 5 sentence passages that they listened to. The passages contained two adjective noun phrases each. So in these noun phrases, we varied the order of the adjectives to be either canonical, so basically in line with what we would expect, so huge grey elephant, for example, or they were inverted to be non-canonical, so grey huge. And we had 2 speakers who recorded the passages for us. One speaker we basically referred to as the canonical speaker because this speaker produced approximately 70% canonical orders of the adjectives, whereas the non-canonical speaker sort of had that flipped ratio, produced approximately 70% of non-canonical orders. So that was how we wanted to essentially vary the predictability of these sequences. And at the same time, I guess, give people a learning opportunity because they were tied, this variability was tied to the different speakers. We ran two experiments, both with young adults here with a combined sample size of 85. So hopefully a relatively decent sample size to be looking for individual differences. What we expected was that unexpected orders would yield prediction error signals, so essentially increased N400 effects, and that the speaker manipulation would sort of modulate the precision of these order-related predictions. What we were then interested in was how closely the N400 amplitude would actually track input predictability. So we were interested in how readily individuals would adapt their established predictive model based on the intra-experimental sensory input. Okay, so this now really gets at the heart of that question: how much do I actually trust my model, and how willing am I to adapt it? So we hypothesized that readiness to adapt might be more pronounced in low idea density individuals because they have a lower precision of their language model, and then also individuals with a flatter aperiodic slope. This was based on the findings by Dave and colleagues, right? The idea being that stronger predictive processing, is associated with a steep aperiodic slope. So we thought maybe these people with a steeper aperiodic slope might also sort of stick more closely to their established predictive model. The way we approached this was we wanted to track trial by trial changes in predictability. And I don't have time to go into the details here, but basically we used word vectors and some clustering techniques to come up with empirically determined adjective classes. And you can sort of see one example here. You see the color adjectives come out quite nicely, for example, which was nice. And then we used these clusters to calculate cluster level surprisal using a bigram model. So essentially how surprising adjective 2 is in the context of adjective 1. We had two measures of surprisal, one which we call global surprisal, which was just based on a corpus. And then we had a measure, which is going to be more important here, called speaker-based surprisal, which basically was a trial by trial cluster level measure for each speaker. So it was determined for each speaker, for each trial going through the experiment. So basically, the idea was this tracked how the probabilities changed, the surprisal actually changed based on the exact sort of sequence of stimuli that participants had been exposed to in the experiment. All right, now let's get to the results. First of all, I just want to show you a quick sanity check, because one issue, of course, here is that when we're looking at these continuous predictors of something like N400 amplitude, it's quite hard to actually show traditional grand average ERPs, right? So it's always good to have some sort of a sanity check to know that we're actually seeing something that's expected within this kind of experimental context. And we looked at that in terms of the effect of word frequency, which shows us an N400 as expected, and also of global surprisal, so corpus-based surprisal, where we also see an N400 effect for a higher surprisal, a second adjective as expected. So that's nice. Looks as though the experiment sort of worked, at least in some way, for what we would expect to see. And then I just want to introduce you to these figures, because this is what I'm going to be showing you for the remainder of the results that I'll be presenting. So these are basically the fitted values from linear mixed model analyses of single trial N400 amplitudes. And we'll typically have sort of a continuous measure along the x-axis. Here it's just unigram frequency, so corresponding to this plot over here, and then basically fitted N400 amplitude on the y-axis. So you can see here that quite nicely as our, this is basically z-scored unigram frequency. As that decreases, we see a more negative N400 amplitude, okay? And the shading shows you a 95% confidence interval. This is the global surprisal measure, where we see also the expected effect, right? Higher surprisal, more negative N400 amplitude. So hopefully these figures make sense. Let's look at something more interesting then. So let's have a look at the effect of speaker-based surprisal over the course of the experiment. So the analyses here are very similar, showing you here now essentially very similar sort of plots to the ones that you saw on the previous slide, but now just showing the beginning, the middle, and the end of the experiment. Should add all of these sort of trichotomizations that you're going to be seeing here in terms of things like stages of the experiment, and then also individual differences, measures, and later age. These are just for visualization purposes. All of these continuous predictors were actually entered as continuous predictors into our mixed model analysis. So what we can basically see here is that by the end of the experiment, we see a very nice alignment between N400 amplitude and speaker-based surprisal, right? So the higher our speaker-based surprisal measure, the more negative, the more pronounced our N400 amplitude. And this seems to entirely override the whole canonicity manipulation by the end of the experiment, right? So we see that N400 amplitude attunes to speaker-based surprisal over the course of the experiment, which is quite nice, right? So people are adapting their models to reflect the input that they're getting in the experiment. But does that actually differ between individuals? Let's have a look at our individual differences measures. Here's the result for idea density. And sorry, these plots are sort of getting successively more complex, but again, they're just the same as what I showed you before. Now we're looking at beginning, middle, and end, our effective speaker-based surprisal on the N400, and now just looking at people with a lower idea density, sort of a medium idea density and a high idea density. And sort of in line with what we were expecting, we actually found a higher, a more pronounced N400 amplitude adaptation to speaker-based surprisal for lower ID individuals. So you can sort of see here that alignment between N400 amplitude and speaker-based surprisal is stronger for the low ID individuals. For aperiodic slope, the result was actually the opposite of what we initially expected. We found a more pronounced N400 amplitude adaptation to speaker-based surprisal for those people who had a steeper aperiodic slope as opposed to a shallower aperiodic slope. And I'm going to start with this result in terms of trying to offer an explanation. So just to reiterate, we saw stronger predictive processing in the sense of this more flexible sort of model updating. Okay, so basically, perhaps our initial interpretation of Dave and colleagues' results was not quite right, in the sense that, you know, we originally thought, okay, stronger predictive processing might mean a more rigid predictive model, but when you sort of think about it, it could actually also reflect a more flexible predictive model, right, that you can update more readily to changing circumstances. And there may actually be again, a neurophysiological mechanism that underlies this, that gives us some sort of an idea of what's actually happening in the brain to facilitate this. There's one study, at least, that has shown that this notion of neural noise, as can be measured by aperiodic slope, is actually related to neural gain, which is modulated via the noradrenergic system. So a gain modulation basically means that with higher gain, you have a stronger sort of discrimination between excitation and inhibition. When you think of this sort of as a response curve to, you know, say switching on to a relevant stimulus, you know, say think of a go, no-go task, and switching off to an irrelevant stimulus, you can see that with high gain, which is here in the dotted line, that distinction is very sharp, whereas with lower gain, that distinction is not as sharp. So steeper aperiodic slopes are associated with high gain, and we reasoned that perhaps this is associated with a more effective discrimination between relevant and irrelevant information. So maybe with a steeper slope, people are able to distinguish those sort of categories more sharply within an experimental context. And so maybe they're able to sort of have those changes in precision weighting more readily as they're learning in an experimental environment. So that was a tentative explanation for aperiodic slope. For idea density, we saw, as we had sort of expected, that people with a higher idea density show with a lower idea density, that these people show a faster model adaptation to current contextual information. And even though we'd sort of predicted this, it does to a certain extent seem counterintuitive, right? Because as I mentioned, in the context of the Nun study and other studies, low idea density has been identified as a risk factor for cognitive decline and dementia in old age. So why should these individuals actually be showing what we might think of as a good strategy, right? A fast adaptation strategy. But again, taking a step back, we might ask whether fast adaptation is actually a good strategy. We sort of had no measure of utility in terms of which strategy was more useful in this kind of experiment. Because really what people are doing here is they're sort of abandoning a lifetime of language experience within a very short exposure period. So maybe this equates to this sort of idea of overfitting that we talked about in the context of aging. Maybe adapting too much is actually not really a good thing. So the hypothesis that this gave rise to is that this potential strategy of rapid model updating that we've seen in individuals with a lower idea density could actually amount to a strategy that ends up being suboptimal in older age. So basically that's in contrast to what we saw being described by Moran and colleagues, where they essentially suggested that optimal aging actually amounts to reduced sensory learning, so reduced model updating. So this then led us to have a closer look at what actually happens across the adult lifespan. We ran a very similar experiment to the one that I just showed you, but this time with 120 participants aged 18 to 83. So the language processing task was equivalent. We had a whole sort of battery of cognitive tests that I won't talk about today. Also a brief auditory oddball paradigm to sort of have a look at these more basic, I suppose, measures like the MMN. And then we also looked at similar resting state EEG measures and idea density as well. Our hypothesis was that we would see more pronounced model adaptation, more pronounced sensory learning in younger adults, in line with the existing literature from the MMN. And we were interested, in addition, as to how this might be influenced over and above age by our individual differences predictors like idea density and 1/f slope. Now, in addition to 1/f or aperiodic slope, in this study, we also looked at aperiodic intercept, which is basically the second parameter that can be used to capture aperiodic activity. So this is, again, just sort of showing you a schematic here of what aperiodic activity looks like. We sort of looked at the slope before, right? So basically how steep this curve is. But there's also the aperiodic intercept, or sometimes also called the offset, which is basically the power predicted for the lowest frequency bin. So sort of how high or low this offset is here. And these two parameters vary, both vary. They are correlated, but they can vary independently of each other. As you can sort of see here, the slope can vary, but also the offset or intercept can vary. Now, less is known about the intercept than about the slope, but it is thought to reflect aggregate population spiking activity. It's known to correlate with the bold response in fMRI, and it is also reduced with increasing age, much like the slope flattens. Okay, now for the auditory oddball task, I don't want to go into detail here. It's just because I will be using these results a little bit later. I do just want to show you that we found a nice MMN followed by a P3 for our oddballs in comparison to our standards. And we found this for all of our three age groups with some interesting differences to how these two effects change over time over the course of the experiment, but don't have time to go into the details here. All right, let's move on to the main language task. So remember, this is basically the same task as the one that I showed you before. So we're looking at this measure of speaker-based surprisal over the course of the experiment with the question of how do the N400 effects align with speaker-based surprisal? Do people adapt their predictive models to the input and the individual speaker-based input that they're getting in the experiment? Now, what we see is that for young adults, we see that pattern of adaptation that I already showed you from the first experiment, right? So you can see for the blue line here, By the end of the experiment, we have a very strong alignment between N400 amplitude and speaker-based surprisal. We see a similar but somewhat attenuated pattern for the middle-aged adults, where we still see that adaptation, but it's not quite as strong. Whereas for the older adults, we don't really see it at all. If anything, there's even a slight reversal. So this confirms, first of all, the most basic hypothesis, which was that we expected to see stronger sensory learning, so stronger model adaptation to the intra-experimental contingencies for our younger adults. Okay? But we were also interested, of course, in the extent to which our individual differences predictors would actually show us anything useful over and above these effects of age. So basically what we did was we residualized the individual differences predictors on age. So basically just looked at the proportion of variance in those predictors that was not explained by age, and then added those to a model that also included age. Let's look at idea density first. While it did improve model fit over a model just including age, when we sort of look at the pattern of the results, it doesn't really seem to illuminate very much. So if we look at the younger adults here, for example, we in this particular case, once we've taken age into account, we don't see a lot of difference based on idea density. And again, also for middle-aged and older adults, a lot of overlap in terms of confidence intervals. So yeah, it's not really clear what idea density is contributing here. For aperiodic activity, we've got slope on the left and intercept on the right. Sorry, I know this is a very busy figure, but bear with me. Let's just look at the young adults to start with for slope. So we can sort of see here that over and above the effect of age, we do still see that effect that we saw in the first experiment, right? That young adults with a steeper slope show this higher propensity for model updating for alignment with the sort of probabilistic structure of the experimental input by the end of the experiment. Whereas for older adults, we actually see a somewhat surprising sort of inverse effect. They're sort of showing an inverse surprisal effect for those older adults with a steeper slope by the end of the experiment. For aperiodic intercept, we find that young adults with a high aperiodic intercept, so high aggregate sort of population spiking, also seem to show this sort of faster adaptation, this more pronounced adaptation over the course of the experiment, whereas we don't see a lot going on for middle-aged or older adults here based on differences of aperiodic intercept. So just to summarize, we see that young adults with a higher aperiodic intercept and steeper aperiodic slope seem to show a higher propensity for predictive model updating based on unexpected sensory input. This is over and above the effect of age. So it seems that at least these sort of aperiodic activity predictors are interesting in terms of capturing individual differences over and above those effects of age. And we saw this unexpected tendency for this sort of inverse surprisal effect for older adults who have a steeper aperiodic slope when we're looking at the end of the experiment. So yeah, not entirely sure what to make of that. Let's now just briefly have a quick look at actually what happens when we use the MMN and P3 as predictors. And I'll tell you more about why we did that in just a second. But I guess the most basic reason was that if these markers within a very basic auditory oddball paradigm are already telling us something about the basic sort of information processing tendencies that people have and their propensity for model updating, then maybe we should actually also see this being reflected in our N400 amplitudes, if rather than using these resting state metrics, we actually use individual MMN and P3 amplitude from the oddball task as predictors. And what we see is that if we look at the MMN, which is sort of left-hand panel here, we actually see quite a similar pattern to what we saw for aperiodic slope. So for people with a high individual MMN amplitude, this is the green line, we see that quite strong sort of adaptation to speaker-based surprisal over the course of the experiment for young adults. And we see that unexpected reversal for older adults. Whereas for the P3, again, we seem to actually see a somewhat similar pattern to what we saw for aperiodic intercept, where people with a high individual P3 amplitude, if they're young, they also show this relatively strong sort of adaptation of N400 amplitudes to speaker-based surprise over the course of the experiment, but we see less going on, for example, for the older adults in terms of this particular kind of measure. Now, why might MMN and P3 actually be interesting predictors here? So again, first of all, to recap, we saw that the MMN roughly seems to mirror the pattern for aperiodic slope, whereas the P3 pattern roughly seems to mirror that for aperiodic intercept. MMN, as we've talked about, is an index of sensory learning, and it's thought to reflect model predictions about the sensory input. The P3, by contrast, has been associated with the processing of motivationally significant stimuli, and it has been linked to increased gain control through the release of noradrenaline. What is also relevant here is that P3 effects have been discussed in terms of reflecting prediction errors not on the stimulus itself, but on the context in which it appears. So basically, prediction errors about precision rather than about stimulus content, than about sensory input. So this distinction has been actually equated with a sort of the distinction between first order and second order statistical inferences. So if the MMN mirrors some inferences and predictive processing about stimulus content, that could be linked in terms of, say, statistical inferences to assumptions we might make about, say, the mean of a distribution, whereas inferences about stimulus precision, which is what the P3 has been linked to second order statistical inferences like standard deviation, for example. So the idea was maybe this can actually tell us something about that pattern of what we see in terms of aperiodic slope and aperiodic intercept. So based on this similarity of patterns between aperiodic slope and the MMN on the one hand, and aperiodic intercept and the P3 on the other. So it might be the case that individual differences in aperiodic slope or neural noise might be more strongly associated with these content-based prediction errors, these first-order inferences about the input, whereas aperiodic intercept may more closely reflect differences with regard to these context-based or precision-related prediction errors, which can also be thought about in terms of these second-order inferences. So inferring not only what you're going to be expecting about the content, but also what you're expecting about its precision. We propose that these two mechanisms together potentially define the rate of sensory learning, and that jointly they seem to be reduced in older adults, which seems to avoid excessive model complexity. So the idea here is that noise and aging might have some interesting consequences. Basically, what has been discussed in the literature so far is that there's quite a lot of evidence for noisier information processing by older adults, right? This has been looked at in terms of both higher sort of intra and inter-individual response variability. So we basically see the noise in terms of behavior as well. We see it in terms of less effective neuromodulation, which is then linked to an attenuation of neural gain, as we saw before. So it's sort of all it all comes together. We have more variability, we have less effective neuromodulation, we have attenuation of neural gain, we have a flattening of the aperiodic slope, we have a reduction of aperiodic intercept. But what does that then actually mean? Well, what we would sort of propose based on what we've seen here is that a flattening of aperiodic slope with age may, at least to a certain extent, be beneficial because it may serve a protective mechanism to avoid overfitting and excessive model complexity. Okay, in line with this idea that, you know, having a too complex model as we age is actually not particularly beneficial, perhaps. Now, what about idea density? Yeah, the jury is still out here a little bit. So we saw no correlation between idea density and aperiodic slope or intercept. And in our sort of lifespan experiment, idea density also didn't really illuminate what was going on. So very speculatively, maybe idea density in young adulthood is actually a more useful predictor than cognitive aging, for cognitive aging in comparison to ID in middle or old adulthood, but we don't really know. As I said before, there are some mixed results on how this measure changes across the adult lifespan, and we really don't have good longitudinal data at an individual level. So yeah, unfortunately, even though the overall message of the talk here was that we wanted to look at what's going on with idea density in the Nun study, I don't have a super good answer for you here, and I'm just going to skip this in the interest of time. All right, so yes, I did promise to unravel the mysteries of the Nun study. Have we actually unraveled anything? Well, like I said, things are still a little bit unclear with regard to idea density itself, but I think it at least helped to put us onto something else interesting. So overall, I think what I'd like to conclude is that from our data, it seems to be the case that higher neural noise as associated with aperiodic slope, so a flatter aperiodic slope is associated with lower neural gain and a lower rate of sensory learning regarding stimulus content. By contrast, lower aggregate spiking, which is associated with a lower aperiodic intercept, is associated with a lower rate of learning regarding stimulus context or precision. And jointly, these two mechanisms define a reduction of sensory learning with age, which, rather than being a bad thing, can actually be useful, at least to a certain degree, because it correlates with less complex and more efficient predictive models. And so the proposal here is that this sort of increasing neural noise with age might actually have a protective function. So basically, this would be sort of a functional correlate in terms of reduced model updating for Wojtek and Knight's physiological proposal, where they also said that a little bit of noise is actually a good thing. And maybe, just maybe, what idea density in young adulthood taps into is some sort of individual propensity for rapid model updating, which, in the sense of model overfitting, could then correspond to a suboptimal strategy in old age. And with that, I'll close by thanking my collaborators on this research, and thank you so much for listening.
Thank you so much, Ina. Oh, there we go. Yes, we have a camera way in the back of the room, so people are actually sitting just outside of your view, unfortunately. What I'm going to do... I
can see a couple of people.
Yes, there's more than you can see, I assure you. So what I wanted to do is to open it up for questions first from our room, and then go to online questions that we may have. Anything from our room. Okay. And Ina, if you can let me know if you can hear the question, ask her. Otherwise, I'm going to ask her to come to the mic.
Oh, please be able to hear it. Were there tiers of the ungrammaticality or the unnaturalness of the adjective bigram reversal? And if so, what was the training set or training data that was used to determine that? Because I was thinking large gray versus warm human. There's that range of how unnatural the aversion would be.
Yeah, absolutely. So first of all, I could hear the question very clearly, so thank you. I mean, in a way, that was sort of why we ended up actually veering away from this idea of canonical versus non-canonical, because it actually ended up being quite problematic. So as you already noted, the type of adjective involved in that order reversal can quite profoundly sort of change how natural or unnatural an order reversal is perceived as. And the other problem that arises here is that actually tends to vary quite a lot between individuals as well. So for that second study, we actually had a post-experiment questionnaire where we gave people some of these adjective orders, just sort of a selection, just to try to get a sense of how their sort of individual ratings of them would be, and they were quite variable as well. So that was one of the reasons why we decided to basically base our measure of speaker-based surprisal more just on the probability of encountering these empirically determined adjective clusters in that respective order, rather than trying to base it on measures of canonicity or anything like that. So of course that does mean that I don't have a trial by trial, participant by participant measure of how natural or unnatural people found these things. All that this measure of speaker-based surprise reflects is how expected these orders could be based on how often they occurred for that particular speaker. I hope that answers your question.
It did.
It does, I hear. Yeah.
Yeah.
Okay, great, thank you.
Any other questions from anyone? I think I jumped the gun a little bit with a question online, Ina, because I was, given your introduction, I was expecting you to show us a correlation between the density and the prediction measure. So my question, but I think the question can still be asked. So to what extent do you think other general cognitive abilities like attention and focus are mediating any kind of relation you might find, I should say that now, between precision weighting and idea in sensory incomprehension, and then proposition density in production, or are attention and focus just another side of the same coin, where on the other side you have precision weighting?
Yeah, look, I mean, I think I guess the way that I would think about this now is perhaps more in terms of things like cognitive control potentially, which might relate to this, this sort of idea of gain control as well. The idea that you're basically discriminating between relevant and irrelevant stimuli, which of course then does relate to something like focus or focused attention. It's the extent to which that is actually related to idea density per se is a bit difficult, because unfortunately, even though idea density did lead us down this path, it actually didn't end up correlating with very much at all, particularly in the sort of in the lifespan experiment. So I definitely think that that there's a relation between some of these abilities, these more general sort of cognitive abilities that you described, and this sort of sensory precision weighting, because I think that ability to be able to pick up on which stimulus features in an environment like the one that we had in our experiment, where people were sort of able to learn, I suppose, if they wanted to, what kinds of sequences to expect. I think that the ability to more effectively discriminate between the sort of the stimulus features that are relevant for these environmental contingencies and those maybe that aren't, I think that probably does play a role in what we're seeing here.
I would think that idea density is also a much more noisy variable than the precision weighting, the MMN that you're looking at, right? So measuring that with EEG. So I'm thinking about it also from the perspective of looking at proposition density in a phasic output, for example, which is what we do, where obviously it's a function of all sorts of factors, strategic as well. How do you deal with certain production problems? So it seems to be much less directly reflective, to me at least, of an underlying ability than the MMN would be.
Yeah, and one thing that we found quite consistently was that our electrophysiologically based predictors, so the MMN, of course, on the one hand, but also the resting state measures, they seem to generally outperform anything behavioral, not just idea density, but also some of the cognitive tests that we had, which I didn't have time to go into today. So it's quite astounding because we've been using these resting state measures, and particularly sort of the aperiodic measures, with a range of different studies now, not just on language, and they seem to explain quite a bit of inter-individual variance in terms of task-related electrophysiological patterns. So I think, to me, I completely agree with what you're saying, that the predictors based on brain activity do somehow seem to be a bit more reliable and indicative of individual differences with regard to information processing than what we can measure behaviorally. I would completely agree.
I wonder if you think, if you agree there may be a relation between another language comprehension factor that we've looked at in the past, particularly my student Svetlana Malyutina has looked at garden path processing in older adults compared to younger adults, where we find that older adults are less easily garden pathed because, that was our assumption, very much in line, I think, with the way you were talking about this. They seem to hold on longer to the initial pars and are not so easily swayed by an incoming, apparently syntactically anomalous stimulus. They just stick with the interpretation that they were already having, right? And that seems to be similar, I think, to the way you were talking about, and that's apparently a sign of healthy aging. Right? If you do that, you're aging like you should, apparently.
Yeah, I think that's very consistent. I'll definitely have to I'll have to look that up. So yeah, thank you for that.
Thank you for your time. I don't see any other questions online. We do have a question.
I just want to tack on, because I was thinking too of when an adjective bigram reversal could change the semantic. I mean, could change the proposition, right? Like average 7-day cost or 7-day average cost, right? And so that, I mean, I think with the garden path question, that's a big issue too. That was a.
Yeah.
I mean, I think, I think this is related. I mean, one thing that we've been thinking about is essentially what would happen if the ability to sort of, I guess, update your model in response to these unexpected sort of input instances, where that would actually really be useful, right? So, of course, there are circumstances where the utility of actually doing that model update would be quite profound. So, say older adults learning a new language, or other kinds of sort of learning situations where you want to say that the outcome would actually be, or the desired outcome would actually be that you don't stick to your established model. So I think in a way that's related to what you're asking, right? Because if there's a meaning change, then obviously if you're not going to update your model, then you're going to miss the intended meaning of the sentence. So one thing that I actually really like to do as a follow-up, we just sort of haven't been able to get around to that yet, is to try and sort of design an experiment where we actually have some sort of a sense of the utility of how beneficial it actually is to be adapting your model to what's going on in the experimental input, and to sort of see what happens then, particularly with the older adults as well, whether it's more of a case of when there's no need to do it, they don't do it, or whether there's actually also an issue that they can't do it as readily, even if it's beneficial.
And in principle, typically the need to learn new things is on young people, right? We don't need to learn new things anymore. I don't know. I don't know. I can't speak to you, but I actually do. So, right. I don't see any other questions online either. Thank you so much. We very much enjoyed your talk. To the online audience, please visit us again in 2 weeks' time for the talk by Alex Sagipko. And we're looking forward to seeing you then. Bye-bye.
Right. Thanks very much, everyone. Bye-bye.